chemistry, that is coordination compounds, and there in the last class we had discussed what all things. The very first thing was what is the difference between coordination compounds and a double salt. Now which of the two remains stable in solution? Coordination compounds. Alright, and if I talk about, if I don't talk about stability, then you will refer to double salt. Give me examples of double salt. More salt or carnallite or potash alum. These are the three examples which are given in your book. Alright. After that we talked about as to the what we are talking about basically in coordination compounds is that we did say that they are surrounded by a certain set of ligands which are generally put according to the alphabetical order. So when you put it according to the alphabetical order here, say here you have the ligands, say L1, L2, L3 depending upon the coordination number. Then there you have a coordination sphere which is associated with it. Just a recap of what we had done last time. So here we have the ligands attached to the metal, and generally it is believed that the bond between the two is a sigma bond generally, because they are directly linked. Whatever is within the coordination sphere is directly linked to the central metal atom, and whatever is there outside is ionizable. Say you may be having say any counter ion, which is like, why am I calling it counter ion? Because this is also attached to the central metal atom, but your ligands are directly attached, and this is some kind of a secondary attachment to the metal ion. Okay. Then after that we talked of the Werner's coordination theory. In Werner's coordination theory we talk of the primary and secondary valence. Alright, the primary valence is the one which is ionizable, secondary valence is non-ionizable. Secondary valence is also known as the coordination number, and the coordination number for any metal ion is fixed. Okay, and the last point was that the ligands are always attached to the metal atoms in such a way that there is a specific spatial arrangement or a geometrical arrangement which we will discuss today. Okay, because they are related to the theories. By and large, in order to affect the in order to explain the type of bonding which is occurring, we talk of different types of theories to explain their structures and geometries. Those theories are many theories have been proposed to explain the structure as to how ligands are attached to the central metal atom. One theory is your valence bond theory. Another theory is the crystal field theory. Then you have a ligand field theory also, and if we talk of the valence bond theory, what is the other theory that we generally talk of? Molecular orbital theory, out of which presently at the present stage for your understanding we talk of only the valence bond theory and the crystal field theory. We will talk about it, and before that we have already got some hint for the structure. How did we get hint for the structure? When we discussed isomerism. When we discussed isomerisms, just to remind you that we discussed two types of isomerisms. You discussed structural and stereo isomerism. So in these are like the by and large names, so I am just putting them quickly. You have the structural isomerism and the stereo isomerism. When you talk about the stereo, there you talk of the geometrical isomers and you talk about the optical isomers. So remember this, these are the geometrical isomers and the optical isomers. When you talk of the geometrical isomers now, you talk of either cis and trans or you talk of FAC and MER. Here with me? We did this last time. So if we can revise it for 5 minutes, just imagine the time of, you get so much time to practice extra questions then. So keep your revision time for the initial concepts that are there here very less. So what you have is geometrical isomers, you have cis and trans. Cis is like the arrangement of the ligands on the same side, trans is on the opposite sides. FAC is when you have three ligands together which can say hello to each other easily. And when you have any other ligand coming in between the other three, then you call it a MER isomer. Alright. Then in optical we have D and L. Remember that this D and L can only be designated experimentally. So you need not remember that this particular form had a D or this particular form had an L. That is dextro and levorotatory. These are totally dependent on experimental observations, whether the molecule is rotating the plane polarized light to the right or rotating the plane polarized light to the left. If it rotates towards the right, then it is dextrorotatory. If it rotates towards the left, then it is levorotatory. And then in structural we had discussed 4. Alright, what were those? The very first one, okay, we can talk of ionization isomerism. In ionization isomerism, one of the ligands can get replaced with the ionizable valence. We call it ionization because the ligands can get exchanged. This question seems to be out of sync, incongruous. So we'll take it a little later. It's incongruous, out of place. So what we have here is valence. I was talking about the structural isomers. So when we talk about the structural isomers, we talk of ionization isomerism. Ionization is the one in which there is an exchange of ions. Then you talk of linkage isomerism. The moment we talk of linkage isomerism, we talk of ambident ligands. Ambident ligands are the ones which have 2 points of attachment. But what is the denticity of ambident ligands? 1. They are monodentate. Then after linkage, we discussed coordination isomerism. Coordination isomerism is the one in which you have 2 coordination spheres. Alright, in which say you have metal in the plus state here and metal 1 and you have metal 2. Here you have ligand 1, say 6, and here you have ligand 2, say 6. So what will be the isomer of this? The metals will get interchanged because the coordination number of the metals is fixed. So in both the cases, if there are 6, you can also have M2 now coming here with your L1 6 and your M1 is coming here with L2 6. So basically there is an entire change in the coordination sphere, and so you call it coordination isomerism. Then the last one that we discussed was solvate or hydrate isomerism, in which the water or the solvent is attached directly. The number of molecules which are attached to the metal atom changes in being directly bonded or indirectly bonded. That means you will have a shift. Maybe you have a water also here. If this was say water, what will happen in the next case? If I have to draw the solvate isomerism for this, I will take water outside. So it will become, I am just drawing the alternate solvate. Because you have any example, just remember that you just have to bring about a little changes here, there, and you will get the other isomer. Keeping the total formula a constant, but the total formula should remain the same. So here in this case it becomes metal, ligand 1 remains same, we get X inside as the ligand 2, alright, and X still remains outside and you have H2O. Why did we get only one X inside? Because the coordination number has to remain a constant. I took 2 randomly, so we have taken 2. Can we say? Hydrate is, yes, you can call it. But one thing is here, why don't you call a solvate isomerism as the ionization isomerism? Because it may or may not keep the ions the same. Right? And here you get an additional water molecule. There it is only the change of ions. But here, complete change of ions. But here you may get a water of crystallization as a separate entity in your products. There that won't be there. So there is a clear cut difference anyways. But the funda is the same, that you have exchange from within the coordination sphere. Right? Now you just repeat it for me so that I can go beyond this particular part. We have 2 types of isomerisms. What are those? Structural and stereoisomerism. What 4 types of structural isomers do you know? Ionization, Coordinate with one another because we are doing coordination compounds, and be loud so that I don't have to repeat. Ionization. Very good. Alright, so these are the 4 types of structural isomers that we have. Then if I talk of stereoisomers, what are the 2 types? Geometrical isomers and optical isomers. Alright, so you have 2 types, and in geometrical you can talk of cis and trans, this you can remember. Fak and Ma. Do you want me to show an example? No. Good. So for optical isomers we have DNL, and remember DNL cannot be remembered. The only thing that you need to remember in optical isomers is that if you have any kind of a structure, say if I talk about any kind of a structure, there you should just know that, because I am talking about coordination, that the metal, say if it has an oxalate group here, has another oxalate group here, alright, and say it has 2 ligands here, L1 and L2. So then in that case you just have to note that the mirror image will be what? It will be metal. You will have L1 here, L2 here, then it's easy to draw the mirror image because you just have to see and just put it accordingly. Ox, and you have another oxalator here, and just pick this structure up and place it on top of it. Imaginary, don't cut the sheet. Alright. You just have to pick it up and just place it on top of it. What will you find? That these will form non-superimposable mirror images. And if the non-superimposable mirror images are there, then you say that your molecule is optically active, or it will be called chiral. Alright. So when will you have an achiral molecule? Achiral molecule will be the case when you have superimposable mirror images. So here when you get non-superimposable mirror images, you would say that the molecule is optically active or it is chiral. So remember these 2 words. Okay. So then I think now we can proceed further and talk about the first theory, that is your valence bond theory. Remember, in case of valence bond theory, it is based on the, that is in case of crystal field. Valence bond theory is basically based on the interaction of the ligands with the central metal atom, and it is like considered to be the top. Now depending upon the coordination number, you will be actually talking about the kind of structure which is getting formed. So it is totally dependent upon the coordination number. Like for example, if you have the coordination number of 4, you've already done hybridization in 11th class, right? So if the coordination number is 4, I am just telling you that if the coordination number is 4, then you can have either sp3 hybridization or you can have dsp2. 4 coordination number hai, तो 4 orbitals will be involved in bonding. So 4 means S plus 3p and D plus S plus P2 makes it 4 orbitals. So don't randomly guess it, you know it. Alright, so it is DSP2. This is again for the coordination number 4. So that is what is it all about. So I will talk about valence bond theory now first. Now when we talk about valence bond theory, the very first important aspect of it is that it concentrates on the valence shell, that is the outer configuration. The important thing is that the central, you know that the central atom already has certain ligands available with it, alright, certain orbitals, vacant orbitals available to it, and those vacant orbital means what? That if it has a D2 configuration, you know that 3 orbitals are totally left vacant. Okay, so I will just put some of the postulates of the valence bond theory. In this case, it chooses appropriate orbitals S, P and D of the metals to hybridize with a set of equivalent energy orbitals, which may lead to different geometries like square planar, you can have square planar structure, you can have tetrahedral structure, you can have octahedral structure, or whatever structure that you have is simply based on the interaction of your ligands with an equivalent energy orbitals like s, p and d, which are available for bonding. For for the d block elements, if I talk about d block elements in specific, you know that d block elements get their 3d orbitals filled. All of you all know that, alright. And then after d orbitals, what we have is, we have 4s, 4p, 4d also available. Remember that these 3 orbitals are also close enough in energy that if required, it uses their vacant space. But then I will just talk about it, that these 4, in fact 3d is also filled to some extent. So when we are talking about the orbitals, what are the orbitals first of all we should know, which are available for bonding? 3d, 4s, 4p, 4d, all are like considered to be close in energy. Say supposedly if somebody comes to stay at your place and you have no space to keep that person, you will look for a place which is nearby, alright. If that place is also filled, then you will look for another place depending upon that. So however you have to look for the closeness in the energy of the orbital. So we have 3d, 4s, 4p, 4d available. Okay, so we know that if 3d is not available, we look to 4s. If 4s is like not available, we look to 4p. So once 4p gets filled, we look to 4d and so on. So remember that these orbitals will get involved in bonding. That's the first thing. The next thing is that the d orbitals involved in bonding may either be inner d orbitals or they can be outer d orbitals, alright. The orbitals involved can either be inner d orbitals or they can be outer d orbitals, alright. So here if I talk about the coordination number, just note it down that if you have the coordination number, what are the geometries which are possible? If it is 4, I just talked about, that means 4 orbitals, and hybridization हमने पहले ही किया हुआ है. 4 coordination number का मतलब कितने ligands होंगे? 4. तो पहला hint तो यहीं से मिल जाएगा. Then the geometry will either be sp3 or it will be dsp2. Alright, let's talk about this first. If you have 5, then the possibility is that you will have sp3d. You do not have dsp3 as any of the hybridizations. So then the hybridization that is possible is sp3d. See, I say no to anything. I don't say no to anything. So in that case, presently it is not found in any of the molecules. So we generally don't talk of it. You look at the several examples which are there, you work them out, and then you will get to know a better answer to that question. But there may be a compound which may be possessing that. So, but no. So here we have sp3, dsp2, alright, and then you have, say for 6, what are the possibilities? You can either have sp3d2 and d2 sp3. Count the total number, that will be 3 plus 3, 6 orbitals available. So that means the number of orbitals participating, the number of orbitals which are participating in your bonding will be equal to the number of ligands. So this is like absolutely clear. इसमें तो कुछ सोचना ही नहीं. अगर 4 ligands हैं तो sp3 होगा, नहीं तो dsp2 होगा. Main यहीं पे ये चीज involved है that your sp3 is, the shape of sp3 is tetrahedral, whereas the shape of your dsp2 is square planar. Square planar क्या होता है? That is your central metal atom is placed on the board. Then you have the 4 ligands also placed onto the board itself. This is your square planar. That means everything is there on the plane of the table on which you are sitting. You have the metal placed there and you have the 4 ligands also placed on top of it. Then when you talk about sp3d, what does it correspond to, with geometry? You have to tell me that. Trigonal bipyramidal. Now you should not forget it. It's 12th standard, don't take it lightly. sp3 is your trigonal bipyramidal. And just to remind you, trigonal bipyramidal, एक बार आप ढंग से सुन लो. अगर if your mind has got rusted, I'll give some oiling to it. As I say, if the metal is here on the plane of the board, Then you have 3 ligands lying on the plane of the board itself. Okay, then 3 ligands are on the plane of the board itself. One ligand is here ahead of the plane of the board and one is at the back. So that means there are 2 ligands which are placed at 90 degree to this plane and the rest are at 120 degrees angle. Is that clear to everyone? For the plane of your table, place the metal on the table. एक ट्राइगोनल प्लेनर बनाओ, ठीक है, फिर एक लिगेंड ऊपर है और एक टेबल के नीचे. This is your trigonal bipyramidal, and remember that your trigonal bipyramidal correspond to sp3d2 and d2sp3 is sp3d, sorry, I am really sorry. For 5 orbitals you have sp3d. तो 5 लिगेंड कैसे लगेंगे, 1 2 3 इधर, एक आगे और एक पीछे. सॉरी फॉर द स्लिप ऑफ टंग. sp3d2 will be octahedral, and octahedral is what? It is called square bipyramidal also. Why square bipyramidal? क्योंकि मेटल टेबल पे रखो, 4 ligands टेबल पे रखो at 90 degree angles, one above and one below. So all the angles are 90 degree. You form a square planar first on the plane of the table. Square planar means that you are forming this metal at on the plane of the board, 4 ligands on the plane of the board, then you have 1 ligand out of the plane of the board perpendicular to it and one behind the plane of the board which is perpendicular to it. So you have ML6 like that. So if your coordination number is 6, the hybridization can either be sp3d2 or it can be d2sp3. In both the cases the geometry can only be one, that is octahedral. Okay, and for octahedral all the ligands are placed at an angle of 90 degrees. The metal ligand bonds, the angle between them will be 90 degrees only. But sp3d2 will be called an outer orbital complex and d2sp3 will be called an inner orbital complex because उसके अंदर हमने d जो use किया है वो 3d वाला होगा. We look into it. Valence bond theory, I repeat it again. Valence bond theory is purely based on the outer valence shell or the valence configuration. The ligands which are coming will interact with an equivalent set of orbitals. ठीक है, जो भी orbitals खाली हैं और जिनकी energy match करती है with that of the ligands interaction, ligands orbitals, they will come and interact with the respective orbitals and then they will result in some kind of a geometry which is based on these hybridizations. And you know, for each of the hybridization you will have a particular geometry. Now just repeat, for sp3 what is the geometry? Tetrahedral. For dsp2 square planar. Please remember dsp2 is square planar. Then if it is sp3d, trigonal bipyramidal. If it is sp3d2, octahedral. d2sp3 which is in a orbital complex, d2sp3. Clear to everyone? Please remember this, and this is very important. Let me tell you another thing is that, let me just take up an example and explain this to you. Eyes on to the board now. Say if I take up an example of say, let me just take up an example of CONH3 6 times, no, I will take up an example of COF6 3 minus. ठीक है? Just understand one case carefully and you will be able to do all the other hybridizations on your own. This is a guarantee from my side. Sorry? I will just let you know. For that, first of all, this table is memorized by everyone now. Depending upon the coordination number, you can fix up the hybridization, and once you know the hybridization, you know the corresponding structure. You know that? Now, say if I talk of COF6 3 minus, ठीक है, सबसे पहले तो the question that came up was what is the atomic number of cobalt. So this is something that you should not be forgetting because I made you do it last year. So what is it? Very good, thank you. Some students do remember, many remember. So what we have is you need to remember the atomic numbers at least, which is very important, and your D block belongs to 21 to 30 is something which is there in range that you should be remembering. That is for the 3D series. You have 21, 22, 23, I don't want a dictation for that, 24, 25, 26, 27, 28, 29, 30. Now the point is that you should be knowing the D block elements which correspond to this. What is that? Skr, tie, kraman, fi, ko, ni, ku, zn. Ni, ku. That's a copper, right? So remember this now. For those couple of students who have forgotten, 1 or 2 students who have forgotten. So it is skr, tie, kraman, fi, ko, ni, ku, zn. And I told you that whenever you feel angry with somebody, this is what you are going to use as a tool. This is called the chemistry tool. So it's like skr, tie, kraman, fi, ko, ni, ku, zn. What is it? Repeat it. Shows how much anger you are carrying. So what you have is, you know this, right? For each of them, you know the electronic configuration also. Let me just help you recall. In this, the electrons are filled according to the Aufbau's principle. What was Aufbau's principle? It was that the electrons will be filled according to the increasing level of energies, or it was according to the N plus L rule also. Now a recap of what you had done in 11th. You have the filling of the orbitals, the one which has a lower N plus L value, that orbital gets filled first. This was called the N plus L rule. What was the N plus L rule? If we talk about 3D and if I talk about 4s. What is your 3D now? 3D is, what is N here? It is 3. What is D? Let me tell you, L, when L is 0 it is S, when it is 1 it is P, when it is 2 it is D. ये तो सबको याद है ना? So what we have is, when I calculate N plus L, N तो हमारा principal quantum number है, that is 3, D की value हो गई 2, so 3 plus 2 is equal to 5. ठीक है, और फिर यहाँ पे N की value is 4 and S value is 1, 0, 0, 0, 0. Sorry, S is 0. So you have 4 plus 0 as 4. So whichever has a lower value of N plus L will get filled first. So naturally what gets filled first? 4s. And then the next thing is that the other rule that decides what is going to get filled is your Aufbau's principle. So I am just giving you half a minute to write down the electronic configuration of all these elements quickly. When you write down the electronic configuration of these elements, what will it be? It will be, you check it out, 1s2, 2s2, 2p6, 3s2, 3p6. अब एक चीज याद रखना कि 3p6 तक 18 इलेक्ट्रॉन्स आर टेकन केयर ऑफ, ठीक है. अब ये बाकी के 21, 22, 23, 24 जो हैं, उसमें 18 के बाद 4s विल गेट फिल्ड फर्स्ट. सो 4s में 2 आ सकते हैं, तो 4s2 सबका है. सो वी राइट इट एज 4s2, 4s2, 4s2 तो सबका ही फिल्ड है ना, तो 4s2, 4s2, 4s2. अब कितने हो गए? 20 हो गए सबके. I hope it's not confusing you because you've done it before. 1s2, 2s2, 2p6, 3s2, 3p6 makes your 18 electrons get filled. Then you have 4s getting filled first. So 4s2 सब में fill होगा, 20 electrons हो गए. अब बाकियों में, अब बाकी के किस में जाएंगे? 3d में, because the choice was between 4s and your 3d. Alright? So 3d. Now if I have to talk about 3d, remember that 3d is an inner orbital. 4s remains as an outer orbital, but because its energy is lowered, it gets filled first. After filling, it becomes an outer orbital only. ठीक है, ये चीज याद रखना. अब ये fill हो गया, अब lower energy में कौन हो गया हमारा? 3d. So I will generally write this as, this will be 3d1, 4s2, 3d2, 4s2, 3d3, 4s2. This is the now outer shell configuration. This will be 3d4, 4s2, 3d5, 4s2. Then you have 3d6, 4s2, 3d7, 3d8, 3d9 and 3d10. Now, this is the way you will generally fill it. Very nice. I can see many of the students telling me that there is something wrong. Where is it wrong? You have it in chromium and copper. Why? Because you know that there is the stability of the half filled and the fully filled orbitals. So what will happen? This will in turn become 3d5 and it will take one electron from 4s. So it becomes 3d5 4s1 because that is more stable. And your copper becomes 3d10 4s1. That is, we talk in terms of the energies which are like distributed. Here again you will get an information about the crystal field stabilization energy, which also gives an explanation for that. Alright, here what we have is first, now the question that remained unanswered last year may get answered now. What you have is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. I covered all? Yeah. So now here this was the electronic configuration. So सबसे पहला काम before you go on to predict the geometry of the d block elements, the very first thing that you should be able to do is you should be able to write down the valence shell electronic configuration for the central metal atom. Now you have cobalt. So let's focus on cobalt. You have cobalt. Cobalt, because hybridization is concept that you know once and you know it for all. So you have cobalt, which is 3d7. 3d7 means this will be 3d7 4s2, right? Right till here. Now the thing is that each of your central metal atom possesses a particular oxidation state. Find out the oxidation state of that central metal ion. What is the oxidation state of cobalt here? That is X minus 6 is equal to minus 3. Why minus 6? Because you have fluorido. You know naming, so I am not going into that aspect at all. It will be hexafluorido cobaltate. Why cobaltate? Because you have a negative charge. So hexafluorido cobaltate, and then you have the oxidation state in the Roman form. So you have 3. So it is, so this is equal to minus 3, and then X is equal to minus 3 plus 6, that is plus 3. Alright, so that means the oxidation state of cobalt is plus 3. So next step is that you write down cobalt with a plus 3 oxidation state and write down the electronic configuration. You know that if the electron now has to be given, it will go out from the outer shell first. And if it goes out from the outer shell, it will be donating it from the 4s orbital, right? Look up onto the board first. So then you have 3d6. Okay? Now it will be giving 3d6. The only thing is 3d6 now means that your cobalt has 3d available, 1, 2, 3, 4, 5 with 5 orbitals available, right? And it has now 4s also vacant available, 4p also is available, and 4d is also available out of the plane of the board. So now 4s, 3d, 4s, 4p are available now. What is the configuration? You have 3d6 as the configuration. Fill it up. What will it fill it up as? 1, 2, 3, 4, 5 and 6. And now you have how many fluoride atoms to interact with orbitals? 6 fluoride atoms. So 6 fluoride atoms means that all these d are already occupied. Let me tell you, fluoride is considered to be some kind of a weak field ligand. थोड़ा समझना इस बात को. If I am talking about a weak field ligand, that weak field ligand will not cause pairing of the electrons. It will not cause the pairing of the electrons. That means अगर कोई strong सा ligand होता, इसका explanation is given better in the next theory. Valence bond theory has a limitation that it does not explain the geometry or the hybridization to a great extent, and it does not explain the reasons behind as to why we are getting it. So presently just understand this, जो weak होगा nature में वो pairing नहीं कराएगा. We'll answer these questions in the next theory. ठीक है? तो fluoride is weak in nature, so it will not bring about any pairing. So it will let it remain like that. But you know, each of the ligand is donating a pair of electrons. This I have told you. That is why it needs one full orbital to interact. So if fluorine has to interact, it will now occupy 4s. How many fluorine atoms do we have? 6. So 1, 2, 3, 4, and where do I get the other 2 from? From 4d. Please understand that there are 5 orbitals in 4d. I am just representing 2 here. So you have fluorine now donating to the 4s orbital, then another fluorine to 4p, then another one to the other 4p's, and another one, and then you have, in many of the books you will find that the ligands are placed within the orbital. It's written as F minus, F minus, F minus, F minus, F minus. That's also one and the same thing. You just need to understand that you need a completely vacant orbital to make it interact. So what will be the hybridization in this case? You check it from the orbital, from where it is interacting. So the hybridization in this case is sp3d2. Okay, sp3d2. And what will be the shape then? It will be octahedral. Octahedral means your CO is here, you have F, 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 F. This forms a square planar with each angle is 90 degrees, and you have fluorine above and fluorine below. Understood? So here you have an explanation for COF6 3 minus like that. And this will be called an outer orbital complex. Why an outer orbital complex? Because it involves the outer d orbital. I will talk about it. You remember that whenever I told you that even if a single electron is unpaired, you say that the molecule will be possessing paramagnetic properties. Here you have how many electrons unpaired? 4 electrons which are unpaired. So you have definitely a paramagnetic behavior. And remember that the magnetism can be measured in terms of magnetic moment, which is generally given by the formula under root of n into n plus 2, Bohr magneton. So you have the magnetic moment as under root of n into n plus 2 Bohr magneton, where n is the number of unpaired electrons, and it is an important parameter, let me tell you, because it is an important parameter. We will take up an example and then we will go to it. Clear with this? Now understand this particular example again. We are talking about how to predict the geometry for any of the structures. When we are talking about the geometries, you have say COF6 3 minus as one of the coordination compounds. Focus will be on the central metal atom. Central metal atom की electronic configuration लिखो. Then you find out the oxidation state. Take out that many number of electrons from the outer shell. If it is CO3 plus, so then it will be 3d6, and if when you fill 3d6, check out whether the ligand now is a strong or a weak field ligand. Then if it is a weak field ligand, it will not bring about any pairing of the electrons, and if it is not causing any pairing of the electrons, then it will proceed or start interacting with the orbitals which are totally vacant. Here in this case the orbitals which are totally vacant are sp3 and d2, and d is of 4d, so that is why we call it an outer orbital complex. Another very important thing is when I am talking about an outer orbital complex, I also note that there are almost 4 electrons which are left unpaired, and because of these 4 unpaired electrons, I will have a magnetic moment associated with my molecule, which will be under root of n into n plus 2, and remember that the spin of the electron is half. The spin of each of the electron is half, and so because you have so many unpaired, even if you have a single unpaired electron because of the weak field ligand, and you know that there could have been a possibility when you have maximum number of unpaired electrons, you call it a high spin complex. High spin complex. So now the name that is generally given when you have an outer orbital complex because of a weak field ligand is also called as the high spin complex, because the spin is very high due to the presence of unpaired electrons. Another important thing that you've seen is that it also has a good magnetic moment, that is, it is paramagnetic in nature because of the presence of the unpaired electrons. Question is, how will we find that the ligand attached to the central atom is weak or strong? That is a very valid question. It is an experimental observation where you get to know that it is obtained from the spectrochemical series, and that spectrochemical series is given in the next theory that we are going to talk about, that is crystal field theory. So this is one of the limitations of the valence bond theory, that it does not actually predict whether your ligand is a strong field ligand or a weak field ligand. It just tells you the hybridization based on the coordination compound and say the magnetic moment. Let me just give you a numerical to explain that, but before that let me just talk about another example. Now say supposedly I talk about not COF6 3 minus, but I talk about CONH3 6, CONH3 6 3 plus. Alright. Now try to work it out quickly. I am talking about now the next orbital, that is CONH3 6 3 plus, and here when I am talking about CONH3 6 3 plus, remember that the first thing that we do is we write down the oxidation state. The oxidation state will be CO3 plus again, because ammonia is 0. The charge on ammonia is 0, ammonia is not 0. The charge on ammonia is 0, so we have CO plus 3, which will again be 3d6. Again the filling of the orbitals will be like this. Now in this particular case, ammonia is a strong field ligand. Now I am again telling you that you cannot predict whether the field is strong, but you need to know the spectrochemical series that we will shortly do. I am telling you presently so that you work it out. Ammonia is a strong field ligand. So what will it do? It will cause pairing of the electrons. If it will cause the pairing or the back pairing of electrons, then in that case this electron will come back and pair with the second orbital that was left unpaired, and this will again come here. Now the next step is that the ligand will come and interact, and if the ligand will now come and interact, you will have ammonia molecules to donate a pair of electrons or interact with one full orbital. So what will happen here? It will start from D2 itself, because you have two 3D orbitals available now. So that is like you have ammonia occupying or coming to the orbitals which are left vacant from 3D itself. So it becomes NH3, 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 NH3 and another NH3. So you have 1, 2, 3, 4, 5, 6 ammonia molecules taken care of in this fashion. And when you are talking about those 6 ammonia molecules, now what is the hybridization? You will start checking it from the filling of the ligands. It will be D2sp3. However, it does not bring about any change in the geometry of the molecule. The geometry still remains octahedral. The geometry in this case also is octahedral. But what is the difference here? You have diamagnetic character because all the electrons are paired. The number of unpaired electrons n is equal to 0. So the magnetic moment in this case will be equal to 0 Bohr magneton. Under root of n into n plus 2 will now be 0 into, that's simply 0 because n is 0. And another thing, now you will call it what? An outer or an inner orbital complex? Inner orbital complex, because now it is utilizing 3D. And because the spin is because of unpaired electrons. Here there is no spin or no electron just left like that. So you call it a low spin complex. Why a low spin? Because all the electrons are paired. So generally your inner orbital complexes are low spin, and that is why your outer orbital complexes are high spin. Here the spin would be 0, because again the spin moment is given by under root of s into s plus 2, where s is equal to half for each electron. Okay. So if you've understood this, try it for NiCl4 2 minus. Try it for nickel Cl4 2 minus. Quickly try it out and I expect you to solve it. NiCl4, remember that you have to first concentrate on the central metal atom. The central metal atom in this case is nickel. Nickel is what? Your 3D8 4s2. 3D8 4s2. Find out the oxidation state of nickel, which will be x minus 4 is equal to minus 2. So x minus 4, 4 of chlorido is equal to minus 2. So x will be equal to plus 2. So that means my nickel is 3D8. Now you need information whether your chlorido is a strong or a weak field. Remember that generally the halogens, fluoride, chloride, bromide are weak field. This is something that you will now remember and you will be able to solve it better. So now what we have is, what we'll have here is that we'll talk about 3D8. We know that 3D is available. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7 and 8 is the configuration where 2 are left unpaired. Then you have 4s, 4p and you have 4d also available, 4d, 4p, you have 4s. Remember that d orbital has 5 degenerate orbitals, so I am not showing it completely for 4d, but you can understand it for yourself. For 4s, if I have to talk about, I am telling you chlorido is a weak field ligand, so it will not cause the pairing of the last 2 unpaired electrons. So in this particular case, you have 4s to be, you will start having the chlorido coming in from 4s orbital itself. So you will have Cl1, Cl2, Cl minus 3 and Cl minus 4. So the hybridization in this case will be sp3. Hybridization in this case will be sp3, that is tetrahedral. Very nice. What about, is it an outer complex here? You can just call it because no inner orbital is involved. What about if it is outer? It is a high spin complex. And what is the, find out the magnetic moment also. The magnetic moment in this case will be what? Magnetic moment will be under root of 2 into 2 plus 2, that's 4. So that will be 2 root 2 Bohr magneton, that is root 2 is 1.414, so you can just have it as 2.828 Bohr magneton. Done? That was very simple, so you do not have to put in a lot of mind. Now because we have done nickel, let's check out nickel for another strong field ligand. This was a weak field ligand case. Remember chloride, fluoride, bromide, जैसे ही देखोगे क्या दिमाग में आएगा कि ये तो weak है, it will not bring about any back pairing of the electrons, and if it will not bring about any back pairing of the electrons, it will form an outer complex which will be high spin complex. Yes. In this particular case, we'll just look into the spectrochemical series, because as it is you will just have to check the spectrochemical series which divides your ligands into 3 sections. I'll talk about them. It's I think somewhere in the middle only. So I will just check that out. We have sp3 here. Now the next one that I'm asking you to do is NiCN4. Alright, cyanide. You have cyanide, so it will be cyanido. In the last class I was even calling it cyano. I've checked it in all your texts, it's like cyanido only. When in international papers you will find cyano also as one of the notation for the ligands. So it will be cyanido. And then you have cyanide is a strong field ligand, I'm telling you. Cyanide is a strong field ligand. So sp3 is tetrahedral, and I hope you remember the angle for the tetrahedral, that is 109 degree 28 minutes or 109.5, and the position is like, if your metal is on the plane of the board, then the earlier case the ligand, that was what? Fluoride. What was the one? Chloride. Alright, chloride. Metal chloride bond is on the plane of the board. One chloride is coming above here. The other, there is only 2 atoms which are located on the plane. All the rest of the 3 are out of the plane. 2 coming to the front like this and 1 going at the back. So it is like this, one coming forward, another going back, and you have another one. Cl, so you will have it like that, right? For the next, yes, now I got the answer for this. NiCN4 2 minus. Cn is a strong field ligand. Strong field ligand means it will cause back pairing, so that will cause your all electrons to be paired now, and you have Cn minus coming in from your d orbital. So 1 Cn minus, 2 Cn minus, 3 Cn minus, and 4 Cn minus. So the hybridization in this case will be dsp2, inner orbital complex, low spin complex, spin is 0, spin moment is 0, magnetic moment again is 0 because you have total unpaired electrons. So that is why this will be called as diamagnetic in nature. This will be diamagnetic in nature. Also remember that depending upon the number of electrons which are left free, you also have color because of those electrons, that is due to the DD transition. This you will be studying in D block chemistry also, that whenever you have d electrons as unpaired, those unpaired electrons are free to move, and because the d orbitals have similar energies, they are degenerate, the electron is free to jump from one d orbital to another d orbital, and because of this jumping, jitni energy chahiye for the energy that is required for the electron to jump from one d orbital to another d orbital is the same that corresponds to your visible region. Visible region means 4 into 10 to the power 4 to 10 to the power 7. So you have that range of visible region wavelength, and so you see colors for these coordination compounds also. Now the color will depend upon the number of unpaired electrons which are there. So that is also something that you should be remembering, because you may get for reasoning questions also, why is a particular compound. Now this will not be colored, it may be white. So you will obtain a white powder for tetracyanidonicolate 2. Generally when you check out the powder, so it's generally white in color, and then when you check it out for any other, say had it been nickel tetrachlorido, we did chlorido before, tetrachlorido nicolate 2. So then in that case you will have a color of the compound which will be due to the presence of unpaired electrons. So remember that. Now another thing gets attached, that if you have unpaired electrons, then it will also lead to different colors of the compound, which is a characteristic feature of that particular coordination compound. Right. The one of the questions which is given is like, can be taken up, that if I tell you that your MnBr 4 minus, this is the example taken up from your book itself, MnBr 4 of 2 minus, if the spin moment, spin only magnetic moment, that means spin only, let me just tell you, the magnetic moment for this is given as 5.9 Bohr magneton. The magnetic moment for this is given as 5.9 Bohr magneton. Then you have to tell what is the, predict the geometry. Let's talk about it. So what is the geometry? Seems like exams are over for some students. So what you have is like geometry is here, you have to predict the geometry. तो कैसे करोगे geometry predict? एक तो सबसे पहले you do not have to put in a lot of minds to do it. You know that Bohr magneton is your magnetic moment, which is under root of n into n plus 2, where n is the number of unpaired electrons. Now here in this case you have manganese. Manganese is like 3d5 4s2. Alright, here the oxidation state will be plus 2 only, x minus 4 is equal to minus 2. So oxidation state will be plus 2. ठीक है, so plus 2 मतलब 3d5. So अब दो chances हैं, या तो bromido is bringing about pairing or it is not bringing about pairing. अगर ये pairing कराएगा तो 5 electrons का 1, 2, 3, 4, 5 कैसे होगी pairing? You will have only 1 electron left. So 1 electron means it will be root of 1 into 1 plus 2. So that will be equal to root 2, that will be 1.414 Bohr magneton. 1 plus 2, 3, So that is 1.732, right? That is 1.732 Bohr magneton, which it is not. So that means that the number of unpaired electrons are much more than the total paired. So that means this is a weak field ligand. Weak field ligands means that it will form an outer orbital complex. क्योंकि वीक है, पेयरिंग नहीं करा रहा, 3d5 टोटली कंप्लीट है तो बाहर से फॉर्म करना शुरू करेगा. 4 इज द कोऑर्डिनेशन नंबर. तो 4 कोऑर्डिनेशन नंबर में दो स्ट्रक्चर्स बनते हैं, एक sp3 और दूसरा dsp2. ठीक है, dsp2 इज इनर. वो सिर्फ तभी बनता अगर हमारा पेयरिंग होता और फिर हमारे पास d ऑर्बिटल अवेलेबल होता, राइट. बट बिकॉज d inner orbital is just not available, so the geometry will be sp3. So I am just telling you that you need not work out, क्योंकि कई बच्चे क्या करेंगे, they will start working out the number of unpaired electrons and then that will take a lot of time. See, there are two chances, either you will have one unpaired electron or you will have 5 unpaired electrons. यही चांस है, क्योंकि 5 electrons d5 configuration है, तो पेयरिंग होगी तो एक अनपेयर्ड रह जाएगा और नई पेयरिंग होगी तो 5 अनपेयर्ड रह जाएंगे. 1 वाला केस है ही नहीं, बिकॉज द मैग्नेटिक मोमेंट इज हाई, इट इज वेरी हाई, इट इज फॉर्मिंग अ हाई स्पिन कॉम्प्लेक्स, आउटर ऑर्बिटल कॉम्प्लेक्स. एंड आउटर ऑर्बिटल किस केस में बनेगा, dsp2 तो इनर है, तो sp3 इज द आंसर. गॉट दिस? So this is like an easy thing. This is how valence bond theory actually predicts your talks about the prediction of the geometries. So it is some kind of a vague thing that you look at the coordination number and then you predict the geometries based on that. So there are a number of limitations of the valence bond theory. Let's talk about the limitations of valence bond theory. The limitation, the very first limitation is it involves many number of assumptions. There are many assumptions in it. The next is that because of these assumptions there is no quantitative description, no quantitative interpretation of the structures, and it does not explain why a particular color is obtained for a particular geometry, why a particular color is obtained for a particular geometry. Next is it also does not give any hint about the kinetic or thermodynamic stability. It does not tell you anything about the kinetic or the thermodynamic stability, right? And then kinetic or thermodynamic stability, it does not make an exact prediction. Exact prediction for structures which are like similar, like if you have sp3 hybridization, it can either be tetrahedral or it can be square planar. Now don't get confused, it can either be tetrahedral or square planar, so it does not give any exact prediction. And last but not least, you have another one which is like it does not distinguish between your weak field ligands and strong field ligands. There is no explanation for why a particular weak is weak, as there was a doubt, why weak is weak and strong is strong. So it does not give an explanation why weak is weak and strong is strong. So here a repetition of your valence bond theory. Remember that when we are talking about the valence bond theory, the focus is primarily on the valence bond, valence shell. You have to look into the outer electronic configuration, for which you need to remember all the elements from 21 to 30, that is your D block series. Presently your focus will be on these only. As you do D block chemistry, remember that you have scandium, yttrium, lanthanides and actinides. So as you remember your D block, which you will do in D, remember if you have 3D1, the lower one will be 4D1 and the lower one will be 5D1. So their behavior will be similar to these. So we are doing the primary thing, which is like the upper period, which will help you understand the lower ones later. Here the thing is that what will you do after find out the oxidation state of the central atom? After finding out the oxidation state, you just give away those many number of electrons. After giving that away, you have to check whether your ligand is going to bring about pairing or no pairing. Okay, then if it brings about pairing, then it will be an inner orbital complex, which will be low spin complex. Anything else? Then after that, if we are talking about a weak field ligand, then it will cause no pairing. So a high spin complex and outer orbital complex, and remember that the magnetic moment will be high, so it will be paramagnetic and will also possess different colors. The colors are explained on the basis of the number of electrons which are left vacant, left unpaired, sorry, the number of electrons which are left unpaired. These unpaired electrons have the ability of jumping from one d orbital to another d orbital, and because of this dd transition you observe colored compounds. How will we find that the ligand is attached to Hodan? How can we calculate magnetic property and unpaired electrons easily by seeing at the complex coordination compound? It is very simple. If you have understood this, can we proceed? We will talk about it now. Now we move on to the next theory which gives a better explanation. That is the crystal field theory. There are some by and large important things that you need to understand. Let's talk about this. Or before I move on to the crystal field theory, let me answer this question first. How can we find out the magnetic property? Magnetic property is if you know the number of unpaired electrons. The number of unpaired electrons will be known from the electronic configuration. You straight away what you do is you find out the oxidation state first, M2 plus or whatever. Just find out the oxidation state. If M2 plus happens to be say 3d5, then you just have to look at the ligand. पूरा solve करने की उस time पे ज़रूरत नहीं है ना, अगर आपको सीधा electrons का बताना है तो just write down the outer electronic configuration, that is 3d5. Now if you have to talk about the ligand, just look whether the ligand is strong field or weak field. That you will get to know now when we do crystal field theory. If strong field, then you know it will be only one unpaired electron. If it is weak field, then you have all the 5, and then you calculate the magnetic moment. So just by looking at the complex, ध्यान कहाँ होना चाहिए? सिर्फ central atom पे, and then ligand will come into the picture to find out how many unpaired electrons are left. So that way we can easily find it out. Okay. Next we move on to the crystal field theory. A crystal field theory gives a better explanation of the same thing. You've already seen as to how can we give explanation to say how can we explain a certain, the last limitation of VBT was that we can you cannot distinguish for a particular structure, and no proper explanation is given for that unless and until you have the experimental magnetic moment. अब जो question which is picked up from your text only, the question states that you are given the magnetic moment, ठीक है, magnetic moment experimental observation है कि वो इतना magnetic Bohr magneton is the magnetic moment. From that you were able to now predict, but not from valence bond theory. But for crystal field theory that we will now do, but for the crystal field theory that we now do, now understand वही complex है but approach understanding की different है. क्या approach है crystal field theory में? You have a metal atom and the ligands are approaching the central metal atom. Alright, when the ligands are approaching the central metal atom, they are considered to be purely electrostatic forces. What are the electrostatic forces? They are the ones which are formed by the complete transfer, ionic kind of a bond. So here one important thing is the ligands are considered to be point charges. ठीक है? If they are considered to be point, ligands are considered to be point charges. So if they are point charges, then in that case they will interact, they will have electrostatic forces of interaction. Metal और ligand का relationship कैसा होगा? जैसे electrostatic bond का होता है. ठीक है? And then another thing is that all the 5 orbitals are considered to be having देखो initially हमारे पास d orbitals होते हैं. I am just giving an explanation for that. If I am talking about d orbitals, what are the 5 d orbitals that we have? We have dxy, dyz, dzx, then you have dx square minus y square, and you have dz square. If you remember, when we did atomic structure, we also looked at the different kind of say the contours that these are forming. If I talk about dxy, ये मेरी x axis है, ये y है, तो it lies between x and y, and you have your, this is your xy in the xy plane. Then similarly you have the yz in the yz plane and zx in the zx plane, ऐसे ही in between the axis. What about the z square? जैसे अगर ये मेरा z है, ये मेरा y और x है, dz square is about the z axis like this. This is your dz square. ठीक है, सिर्फ याद दिला रही हूँ, d orbitals आपको पता है. And what about your dx square minus y square? That is around along x and y axis. ठीक है, ये चीज समझ में आई. अब क्या होता है कि जब हमारा crystal field gives a very beautiful explanation, normally you know that your 5d orbitals are degenerate. Degenerate means that they possess almost same energy. That means they are like this. They are like at the same energy levels. When you have more than one energy states at the same energy level, you call them degenerate. So D के जो ये पांचों हैं, they are almost at the same energy level when the ligand is approaching the metal atom. ठीक है, when the ligand is approaching the central metal atom, it will remain, it will cause the d orbitals to remain degenerate only if there is a spherical and an equal environment being created to interact. मतलब if your ligands are coming towards the central metal atom के पास क्या है, 5 d orbitals है. ठीक है, when it approaches those d orbitals, what happens, these d orbitals all of them interact differently. How differently? Say if the approach is such that the ligand is coming from about the bond axis, then the maximum repulsions that will be suffered will be from the d orbitals which are located exactly about the axis. जैसे dz square और dx square minus y square है, इनका शेप कैसा होता है, they are along the axis, और बाकी के जो तीन हैं they are in between the axis. तो होता क्या है, when the ligand is approaching, these two suffer from maximum repulsions. ठीक है, now because these two suffer from maximum repulsions, तो क्या होगा, इनकी एनर्जी बढ़ जाएगी. If they will suffer from maximum repulsions, the energy will increase drastically, and if the energy for them will increase drastically, what will happen as a result of that? If the energy will increase drastically, first of all, this d orbitals, the d orbitals will be, say they were initially at this level, 1 2 3 4 5, all right. These d orbitals will be raised higher in energy because of interaction with ligand. As it is, जब भी interaction होता है, जो हमारा original energy होता है वो थोड़ा सा बढ़ जाता है. So now the d orbitals have gone higher in energy. Now what will happen? It will cause splitting of the energy levels. How? The two which have interacted directly with or suffered from maximum repulsions will become higher in energy. That means two of my orbitals, कौन से, dz square and dx square minus y square, they rise above in energy. That means they will suffer from an increase in energy. Naturally, if I slap one of you, you will gain a lot of energy, and what will happen as a result of which the energy will increase suddenly. So this is what happens, they suffer from maximum repulsions from the incoming ligand, because of which their energy goes higher, alright, it increases. And the other three, they suffer from the same, not the repulsions, but as a result of that increase, they suffer from a decrease in energy, because of which they are pulled down lower in energy. So if I call this splitting of energy of the d orbitals is known as crystal field splitting. What do you call it? Crystal field splitting. समझ आया? Octahedral ligands के केस में octahedral कौन सा होगा? sp3d2 या d2sp3. In both these cases you have how many? Generally 6 ligands, क्योंकि coordination number 6 होगा, 6 orbitals involved हैं, 6 ligands होंगे. तो if you have 6 ligands approaching the central metal atom, then you see that 2 orbitals, they और आपको पता है कि what is the approach like? The approach is about the bond axis, where you have, say, from all directions about the bond axis. Bond axis मतलब x, y, z, यही है ना, और सारे 90 डिग्रीज पे होते हैं ligands. ये बात समझ में आई? तो अब इस चीज को दोबारा से समझो, that when the ligand is coming and approaching the central metal atom, they will suffer maximum repulsions from those d orbitals which are along the axis. और along the axis कौन से वाले थे? dz square और dx square minus y square. बाकी तीन तो in between है. तो So octahedral complex के case में what happens is that the maximum repulsions are suffered from them, so 2 orbitals go higher above in energy and 3 are pulled lower in energy. Those 3 form the T2G level, alright, T2G, that's the denomination we used for it, we denote it as T2G, and the upper one is named as EG level, alright. The upper 2, the doubly degenerate, are now dz square and dx square minus y square, they form a separate party above, and then the 3 dxy, yz and zx form separately. So now you understand that here this is known as the crystal field splitting, or represented as delta naught, which is called the octahedral splitting. What is it? Delta naught, which is the octahedral splitting. Another thing is, ये कितना destabilize हुआ, इसको ध्यान से सुनो, ये कितना destabilize हुआ, जितना ये stabilize हुआ. So it rises above in energy by a factor of 3 out of 5 delta naught. Splitting हुई, that's called delta naught, and क्योंकि इसका कितना rise होगा in energy, this center is known as the Berry center, alright, and ये कितना rise होगा, जितना ये the effect of this will come on to this, जितना ये lower हुआ energy में, that is 3 by 5 delta naught, and this has lowered in energy by a factor of 2 by 5 delta naught. In fact, you can put a minus also because this has lowered in energy. So got that point? सिर्फ x से नहीं करेंगे, एक्सिस से अप्रोच करें, हाँ, they will get dx square, that is because of दो एक्सिस नहीं मिल रहे हैं, वो ऑर्बिटल्स दो नहीं ले रहे हैं, इंटरैक्ट तो वो जहाँ जहाँ खाली मिलेगा वो वहाँ वहाँ इंटरैक्ट करेंगे, बट व्हाट इज द इफेक्ट ऑन द डी ऑर्बिटल्स. जब लिगेंड आपके मेटल के पास आ रहा है, कौन से ऑर्बिटल ज्यादा रिपेल करेंगे, सबसे ज्यादा कौन से रिपेल करेंगे, एक्स स्क्वायर माइनस वाई स्क्वायर और जेड स्क्वायर. हम फिलिंग या उसके ऑक्यूपेशन की बात तो कर ही नहीं रहे कि वो कहाँ जाके बैठेगा, वी आर टॉकिंग अबाउट हाउ दे विल गेट रिपेल्ड. Alright, so this is how this interaction is there, and now based on it, let me tell you, if you have to find out the energy, crystal field stabilization energy, तो ये मैं एक shortcut में बता रही हूँ, there is something which is known as crystal field stabilization energy. ये कैसे find out करते हैं, जितने electrons जिस orbital में हैं, मान लो if you have 2 electrons here, what will be the energy, it will be 2 into minus 2 by 5 delta naught, okay. If you have 3 electrons here, 3 into minus 2 by 5 delta naught, plus अगर ऊपर भी हैं तो accordingly, and ऊपर वाले will be multiplied with 3 by 5 delta naught. Do you understand that? So that way you can calculate the crystal field stabilization energy depending upon how the electrons are occupying. So this is like an extra thing that I am telling you. First of all, this splitting of the d orbitals into 2 levels, that is T2G and EG level, is known as the crystal field splitting, and this splitting from the Berry center is computed as 3 by 5 delta naught destabilization energy and minus 2 by 5 delta naught is the stabilization energy for your T2G level, and 3 by 5 delta naught is the destabilization energy for the EG level. ये समझ में आया? Berry center is the level where your originally d orbitals were degenerate. When the degeneracy was 5, now the degeneracy has got now split. You say that the degeneracy has been lifted because of the incoming ligand. The energy will be different. अगर यहाँ पे, so this energy is different and this energy is different. This one? This is like further lower in energy, so forget about that. This is very 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 low in energy before interaction. क्योंकि अगर कोई आराम से बैठा है तो आराम से बैठा है, जैसे ही ligand आएगा it will get disturbed and because of that it will get higher in energy, right? ligand आएगा नहीं, that depends. अगर strong field ligand है तो it will bring about that pairing and bring about the changes, ठीक है. चार्ज पे नहीं डिपेंड करेगा इस केस में, बिकॉज चार्ज मे बी वन ऑफ द क्राइटेरिया टू डिसाइड द strongness of the ligand. Okay, so let us talk about crystal field theory then ahead. That you have in crystal field theory, you understood this, that it will bring about splitting. Remember that the interaction between metal and ligands will be that such that you talk about the electrostatic forces. Ligands are considered to be point charges. Then you have the conversion of the d orbitals into different sets of d orbitals like T2g and Eg. The splitting between these is known as octahedral splitting. Similarly, for tetrahedral splitting, let me just tell you, the tetrahedral splitting follows a reverse order. In tetrahedral, you have the two Egs coming lower in energy and the dx, dy and dz going above in energy, because so if you understand the tetrahedral structure, how is a tetrahedral structure? You have say two bonds on, say you have one here, then you have two bonds say on, let me just take up any example of simply metal, and you have say any ligand Ml4. So you have Ml here, L here. This angle is 109 degree, 28 minutes. 28 minutes. One ligand will be coming out of the plane of the board and one will be going at the back, such that the angle of 109.5 is maintained. तो अब इस केस में देखो, they are not approaching directly from about the axis. They are coming from somewhere in between, because angle इस केस में 90 नहीं है. So what will happen? The reverse order is generally followed for tetrahedral splitting. So for tetrahedral, Eg is pulled lower in energy. So नीचे वालों की energy, नीचे वाले इलेक्ट्रॉन्स की एनर्जी कितने से मल्टीप्लाई होगी? -3/5 डेल्टा टी. ठीक है, समझ में आया? इसको इस टोटल एनर्जी को हम कह रहे हैं ऑक्टाहेड्रल क्रिस्टल फील्ड स्प्लिटिंग एनर्जी, दैट इज डेल्टा नॉट. ये तीन किस एनर्जी से स्टेबल हुए? -2/5 डेल्टा नॉट एंड ऊपर वाले 3/5 डेल्टा नॉट. अब टेट्राहेड्रल के केस में आई एम सेइंग इट विल बी द उल्टा रोल. Eg will be lower in energy and T2g will be higher in energy. तो फिर अब नीचे वालों की energy will be multiplied with -3/5 delta T and the upper one will be destabilized by a factor of +2/5 delta T. और delta T क्या है? The difference between the two energy levels that you have, Eg and T2g for tetrahedral complex. Eg and T2g are the names. T2g is triply degenerate, Eg is doubly degenerate. So it is related to that only. Okay. So then you have say now the factors that determines the orbital splitting energy. Splitting energy depends upon the orbital splitting energy. Splitting energy depends upon certain factors. One factor is the nature of ligand. ठीक है. तो ऑर्बिटल स्प्लिटिंग एनर्जी क्या होता है? जो क्रिस्टल फील्ड स्टेबलाइजेशन एनर्जी टोटल कैलकुलेट करोगे, वो समझ आ गया कैसे कैलकुलेट करोगे? नीचे वाले इलेक्ट्रॉन नीचे वाले फैक्टर के साथ, ऊपर वाले फैक्टर के साथ. सो देन यू हैव दैट डिपेंड्स अपॉन द नेचर ऑफ द लिगेंड्स. सेकंड इज इट आल्सो डिपेंड्स अपॉन द ऑक्सीडेशन स्टेट ऑफ द मेटल आयन. क्योंकि अगर मेटल आयन टेट्राहेड्रल बनाएगा तो उस केस में हमारी स्प्लिटिंग एनर्जी विल बी डेल्टा टी. अगर वो ऑक्टाहेड्रल बनाएगा तब हमारा स्प्लिटिंग डिफरेंस इन दी डेल्टा नॉट विल बी डिफरेंट. एंड हाउ विल दे बी डिफरेंट? आई विल टेल यू. डेल्टा टी इज 4/9 टाइम्स डेल्टा नॉट. दैट मीन्स टेट्राहेड्रल स्प्लिटिंग इज इक्वल टू 4/9 टाइम्स डेल्टा नॉट. एक्सपेरिमेंटली. So we have delta T as 4/9 delta naught. What is the relationship between delta T and delta naught? बताओ, देख के बताओ. Delta T is equal to 4/9 delta naught. Repeat it 5 times as I move to the board. जल्दी जल्दी जल्दी. Delta T is equal to 4/9 times delta O. That means tetrahedral splitting is equal to 4/9 times डेल्टा ओ. 2 बार तो मैंने ही बोल दिया, 3 बार बोल दो आप. यस, डेल्टा टी इज इक्वल टू 4/9 टाइम्स डेल्टा नॉट. डेल्टा टी इज इक्वल टू 4/9 डेल्टा नॉट, 4/9 delta naught, where delta T refers to tetrahedral splitting factor and delta naught refers to octahedral splitting. T2G नीचे किस केस में आता है? ऑक्टाहेड्रल. EG ऊपर किस केस में रहता है? ऑक्टाहेड्रल. T2G ऊपर किस केस में जाता है? टेट्राहेड्रल. एंड यू नो द स्प्लिटिंग एनर्जी फैक्टर, कैसे वो करोगे? नीचे वाले का असर ऊपर. So you will have -3/5 and +2/5, whatever. That will depend upon which splitting are you talking about. Okay. Next is like I can give you the electrochemical series also. The spectrochemical series, I'm sorry. The spectrochemical series can also be noted down. It's given in your books as well. See, I minus, Br minus, S2 minus, S2 minus, then you have Cl minus, NO3 minus, F minus, OH minus, OX2 minus, then you have O2 minus, then you have water, NCS minus, pyridine, ammonia, ethylene diamine, NO2 minus, Cn minus and CO. See, the general trend, I tell you how it is like you get it from practice only, because there is no such shortcut to remember. You will actually have to go through it. But remember, कुछ general ligands होते हैं जो बड़े common examples होते हैं, जैसे सारे halogens, halide ions. All the halide ions are generally weak. ठीक है? Here water onwards, then you have water onwards wherever you have nitrogen or sulfur involved. Wherever you have nitrogen involved. Alright, sulfide ion is like again a weak field ligand. Wherever you have nitrogen involved, it is generally a strong field ligand. Let me tell you, this is the increasing strength according to spectrochemical series which have been experimentally determined. Experimentally determined. कोई ऐसे नहीं है कि configuration देख के आप बोलोगे strong है कि weak है. लेकिन crystal field theory has specifically told कि ये strong है, ये weak है. ठीक है? So weak वाले are starting from here and then the strength is going on increasing for the ligand. The strongest field ligand here that is mentioned is carbonyl or the CO. Generally there is a special property of CO also that we will focus on it, and in fact I had prepared so many questions for you that you can practice and get back to me in 2 days time. That's the deadline. You will just be able to, because coordination compound is like if you understand it, you just have to look into the question and you will be able to give the answer. You have to remember 21 to 30 elements, electronic configuration, oxidation state निकालनी आती है, उसके बाद हम coordination number को देख के we can predict the geometry. VBT helps us like that. But अगर वो pairing non pairing है तो हमें CFT की help लेनी पड़ेगी, because from CFT we get to know the information, we get the information whether your ligand is strong field और weak field. Strong field है तो pairing करवाएगा, weak field है तो pairing नहीं कराएगा. What is the first point of energy dependency? When energy dependency for splitting, that is like you have this splitting, was it talking about this orbital splitting? Energy, it depends upon the nature of the ligand. नेचर ऑफ लिगेंड मतलब ये वाली चीज जिसकी हम अभी बात कर रहे हैं. अगर वो स्ट्रॉन्ग फील्ड है तो वो पेयरिंग करवा देगा, दैट इज जितने भी इलेक्ट्रॉन्स अनपेयर्ड है उन सबको इफ देयर इज अ पॉसिबिलिटी तो पेयर करा देगा, एंड अगर वीक फील्ड है तो इट विल लेट इट रिमेन जस्ट लाइक दैट. ठीक है? हाँ, crystal field theory में yes, crystal field theory, this is a part of the crystal field theory which is telling you according to spectrochemical series which ligand will be strong and which ligand will be not strong, weak. Okay, तो ये वाले हैं, तो ये याद रखना, आयोडीन, आयोडाइड, ब्रोमाइड, क्लोराइड एंड फ्लोराइड, ये सब तो वीक हैं ही, हैलाइड सारे वीक हो गए. सल्फाइड साथ में ले लो. नाइट्रेट इज एन नाइट्रेटो इज एन एग्जाम्पल विच इज लाइक अ लिटिल डिफरेंट. बाकी सब में अगर NN है, जैसे NCS है, डेडली कॉम्बिनेशन, वी स्ट्रॉन्ग फील्ड लिगेंड. देन यू हैव CO, CN, कार्बोनिल. थोड़ा थोड़ा इसको बार बार ऐसे देखोगे तो फिर यू विल गेट अ हैंग दैट द स्ट्रॉन्गर लिगेंड्स आर हियर. बियॉन्ड वाटर एवरीथिंग इज कंसिडर्ड टू बी स्ट्रॉन्ग, सो दे विल कॉज पेयरिंग. उससे पहले वाले जो हैं जैसे ऑक्साइड आयन, ऑक्सलेटो आयन, देन यू हैव हाइड्रोक्साइड and all these ions are generally weak. ये बीच के वैसे moderate माने जाते हैं पर pairing नहीं कराते. In fact, ammonia is also considered to be at times considered to be some books say moderate, but then you can consider it to be a strong field because it will cause pairing. Delta naught. ऑक्टाहेड्रल स्प्लिटिंग विल बी मोर, आप ये बोल सकते हो, क्योंकि ये क्या है कि ऑक्टाहेड्रल स्प्लिटिंग क्या है, ऑक्टाहेड्रल स्प्लिटिंग इज कितना वो डिस्टेंस मेंटेन कर रहा है अपने डी ऑर्बिटल्स में सच दैट दे आर फार अपार्ट. ठीक है, इधर एक चीज और नोट करने वाली ये है, क्रिस्टल फील्ड थ्योरी स्टेट्स दैट, एक तो आपकी अगर ऑक्टाहेड्रल स्प्लिटिंग की बात करें, एक वो, ठीक है, अब मान लो आपका स्प्लिटिंग हो गया इन T2G एंड EG लेवल, यही ऑक्टाहेड्रल स्प्लिटिंग में यही करा है हमने. हाउ विल यू डिसाइड वेदर पेयरिंग विल हैपन और नॉट, ये पूरी इंफॉर्मेशन तो नहीं है. सो देयर इज समथिंग व्हिच इज नोन एज पेयरिंग एनर्जी आल्सो. ठीक है, अगर वो पेयरिंग एनर्जी बहुत ज्यादा हाई है, पेयरिंग एनर्जी हाई मींस इतनी एनर्जी चाहिए टू पेयर अप. इफ द पेयरिंग एनर्जी इज वेरी वेरी हाई, तो अगर मैं 5 इलेक्ट्रॉन्स की बात करती हूँ, ठीक है, लेट्स टॉक अबाउट D5 केस. D5 इज लाइक जनरली Mn2+, मैंगनीज D5 है, तो ये चीज़ें जनरली अगर आप अच्छे से 21 to 30 वाला याद कर लोगे तो मुश्किल नहीं होगी. मैंगनीज इज D5. ठीक है, अब मेरे को ये पता करना है कि वो पेयरिंग करेगा कि नहीं करेगा इनकमिंग, तो उसका एक फॉर्मूला, एक थंब रूल होता है दैट इफ योर पेयरिंग एनर्जी इज वेरी वेरी हाई, दैट मीन्स अ लॉट ऑफ एनर्जी इज रिक्वायर्ड फॉर पेयरिंग. तो उस केस में क्या होगा, इट विल गो अप टू EG. Why will it go up to EG? Because pairing energy is very very high. Getting the point? So that means if your crystal field splitting energy is less than the pairing energy, then pairing will not happen. ऐसे नहीं सोच रहा, pairing energy is the energy required for pairing. ठीक है, and if it is the other way around like this, then that means the crystal field splitting energy is less and pairing energy is also the crystal field splitting energy is more. मतलब इन दोनों का गैप बढ़ गया, ये और ऊपर हो गया. डेल्टा नॉट का मतलब क्या है कि ये और दूर हो गए, EG यहाँ हो गया, T2G अगर वो पहले यहाँ थे तो अब वो यहाँ हो गए, तो डेल्टा नॉट हैज बिकम मोर एंड पेयरिंग एनर्जी इज लेस, तो वो आराम से नीचे ही पेयर कर देगा, इतनी ऊपर जाएगा ही नहीं. सो इफ योर क्रिस्टल फील्ड स्प्लिटिंग इज वेरी वेरी हाई, देन पेयरिंग विल टेक प्लेस. ठीक है, सो वन पॉइंट इज इफ डेल्टा नॉट इज लेस देन P, then pairing will not happen because pairing and strong ligands. Strong ligands के केस में क्या होता है, strong field ligands will actually what they'll do, they'll strong field ligands का एक असर तो ये होता है कि उनका octahedral splitting energy is less, so this delta naught will be less. अगर ये less है और उस केस में less in the sense that, no sorry, this delta naught जितना ज़्यादा वो strong होगा उतना ज़्यादा it will cause differences between the d orbital, depends upon the incoming ligand. अगर वो ligand strong in nature है तो वो splitting बहुत ज़्यादा करा देगा, and then your T2G will be much lower in energy and your EG will be much higher in energy. अगर ये ज़्यादा हो गया difference तो अब वो क्या होगा, नीचे it will cause pairing. So then क्योंकि अगर स्ट्रॉन्ग फील्ड है तो वो ऑक्टाहेड्रल स्प्लिटिंग बहुत ज्यादा करवा देगा, और अगर ऑक्टाहेड्रल स्प्लिटिंग ज्यादा करवा दी तो क्या होगा, नीचे ही पेयरिंग स्टार्ट हो जाएगी. सो देन यू विल हैव, इफ ऑक्टाहेड्रल स्प्लिटिंग इज मच मच लार्जर देन योर पेयरिंग एनर्जी, तो देन इन दैट केस पेयरिंग विल हैपन, देन पेयरिंग विल हैपन. समझ आया? पेयरिंग एनर्जी इज द एनर्जी रिक्वायर्ड फॉर पेयरिंग. अगर वो बहुत ज्यादा है तो वैसे ही मुश्किल है, और अगर डेल्टा नॉट कम है तो वो कहेगा कि भाई मैं ऊपर आराम से जा सकता हूँ, तो लेट्स सिट कंफर्टेबली हियर. एंड इफ डेल्टा नॉट इज मच मच हायर, देन इन दैट केस you ऊपर it will be lazy enough to jump up to EG, so then what will it do, the next will come along with the other T2G orbitals only to start pairing up. Clear? Then we have to talk of one more concept, that's called the stability, because let me tell you, crystal field splitting में अब हमने देखा क्या, it considers the metal ligand bond to be electrostatic in nature, it considers that thing. अब because of that we have understood कि ligand का जो approach होगा हमारे d orbital की तरफ, it will bring about splitting. और वो splitting किस basis में होगा, octahedral में सारे angles 90 होते हैं, ligand will approach from the axis वाला side, तो जो दो ऑर्बिटल्स एक्सिस को फेस कर रहे हैं कौन से, dx² minus y² and dz², they will face maximum repulsion and because of that they will rise high in energy. तो Eg चला गया ऊपर which is doubly degenerate and you have your dx² minus y² and dz² higher in energy. और जो बाकी के तीन है इन बिटवीन दी ऑर्बिटल्स जिनका कॉन्टूर था x y y z z x, वो क्या हुए, they became lower in energy, triply degenerate called T2G. ठीक है. अब स्ट्रॉन्ग फील्ड लिगेंड और वीक फील्ड लिगेंड की इंफॉर्मेशन भी हमें कहां से मिली, क्रिस्टल फील्ड थ्योरी से. इट गेव अ स्पेक्ट्रोकेमिकल सीरीज वेयर इट डेजिग्नेटेड स्ट्रॉन्ग फील्ड लिगेंड व्हिच विल ब्रिंग अबाउट पेयरिंग एंड वीक फील्ड लिगेंड व्हिच विल नॉट ब्रिंग अबाउट पेयरिंग. अगर पेयरिंग होती है तो रिमेंबर लो स्पिन कॉम्प्लेक्स बनेगा, क्योंकि जितने इनिशियल इलेक्ट्रॉन्स थे वो सब पेयर हो गए तो लो स्पिन कॉम्प्लेक्स होगा. अगर पेयरिंग नहीं होती है देन इट विल बी अ high spin complex. High spin complex is always outer orbital complex. Clear with this, all of you all? Now it also gives us some information about the stability. क्योंकि VBT का limitation क्या था, it does not give us any information about the stability of the complex. It is very easy to understand also. Just look up onto the board. Then I'll just explain the stability. And here if I have to talk about the stability of the ions, remember that if I talk about, say, how will a metal, if say Ml4 is getting formed, let me talk about this particular coordination sphere which is getting formed. ठीक है. इस केस में क्या होगा, अगर स्टेप वाइज एडिशन होगा तो लेट्स कॉल Ml1, दिस विल फॉर्म Ml1. ठीक है. स्टेप वाइज एडिशन भी हो सकता है. तो नेक्स्ट स्टेप में क्या होगा, Ml1 प्लस L1, एक और लेट मी कॉल इट ओनली लिगेंड, ऐसे कंफ्यूजन हो जाएगी. ठीक है. मेटल प्लस लिगेंड इज फॉर्मिंग Ml1, एक लिगेंड लग गया. मेटल लिगेंड, अब इसी के पास नेक्स्ट लिगेंड लगेगा तो अब ये क्या बन गया, Ml2. देन Ml2 में थर्ड लिगेंड लगा तो क्या बन गया, Ml3. Ml3 में नेक्स्ट लिगेंड लगा तो इट फॉर्म्ड Ml4. ऑलराइट. सो बेसिकली इट इन्वॉल्व 4 स्टेप्स to form Ml4. ठीक है. एक और तरीका है, I can talk about what is your stability constant or the equilibrium constant in all these cases. The equilibrium constant, let me call it K1, K2, K3 and K4. Equilibrium constant all of you all know from chemical equilibrium. Now again 11th concept being used here, that will be Ml1 concentration upon M concentration, L concentration. Next will be Ml2 upon Ml1 into L. K3 will be Ml3 upon Ml2 into L, and your K4 will be what? It will be Ml4 upon Ml3 into L. ठीक है. Now if we talk about the formation of Ml4 in a single step, what will that be? M plus 4L giving Ml4. ठीक है. Let me call this stability constant or the equilibrium constant to be a little different. In that case, let me call it beta. Then beta, that is K, whatever you can call it, this will be equal to Ml4 upon M into L to the power 4. And if you check out, multiply all these equilibrium constants K1 into K2, your Ml1 will get cancelled. K1 into K2 करेंगे तो Ml1 cancel हो जाएगा. Then that into K3 करेंगे तो your Ml2 and Ml2 will get cancelled, and that into K4 करेंगे तो Ml3 and Ml3 will get cancelled, and then you will have your basically beta to be equal to, I mean that K1 into K2 into K3 into K4 will be just Ml4 upon M into L to L into L into L into L, that is L to the power 4, which means that your beta, that is the stability constant for any metal ligand complex, will be equal to the stepwise stability constants for each of them. It will be K1 into K3 into K4. So supposedly if you were talking about the formation of a complex with n coordination number, तो उस केस में हमारा stability constant बीटा क्या होगा, K1 into K2 into so on till Kn. Alright, this is another information that is important, that gives you about the stability constants. One more concept very importantly, I told you we will be talking about CO, which is one of the most, how stability is linked to this. You have, generally you measure the log values, okay, log beta value and log K values. If your log beta value is very high, then you say that the stability is very, very high. Alright, you generally link it to stability constant values. I will just check up if any example is like provided here. Stability constant, just check up that you, then it is considered to be stable. And remember that whatever your log beta value is, the reciprocal of that is your instability constant. Alright, that is called the instability constant or the dissociation constant. It is defined as the reciprocal of the formation constant or the stability constant. Like the information given here is that formation constant, and see, I tell you, log beta value for your Cu NH34 is generally given as 11.9, and this is the experimental value. Log beta value taken from your text only. So it is 11.9. It is 11.9 which is generally high. अच्छा, इस चीज़ में ना एक ऑब्जर्वेशन ये है कि log k into log k2 into log k3 these values go on decreasing. इसका मतलब है जितने और ligands आते जा रहे हैं उनका approach is even more difficult, and you understand that chemistry now. क्योंकि और ligands आएंगे तो because of repulsion that stability thing will go on getting reduced. ठीक है, that stability will go on. Log beta. Log beta is, it is the stability constant, and generally you call the beta also a stability constant. Generally whenever we look at the stability constant's value, we look at it in terms of log beta. Beta is the stability constant, and the reciprocal of the stability constant is known as the instability or the dissociation constant. Alright, now before time gets up, there is another very important concept which is left for us to understand, and then it is a humble request to all of you all, wherever you are listening to me from, to solve the questions that I thought of doing today. So please make sure that you solve all those questions. It will not take much time. Hardly, I think around 50 questions are there. So solve all those questions and then get back to us with the solution as soon as possible. Right? Last, I wanted to talk about one of the most important ligands, which is a strong field ligand, that is carbon monoxide. You have already done it. We have done the molecular orbital diagram for carbon monoxide. Let me just remind you of that. Carbon monoxide में कितने electrons होते हैं? You have how many valence electrons? 4 plus you have 6 total electrons of carbon, and you have 8 of oxygen, that is 14 electrons. You remember that when we filled up the molecular orbitals, we had the 2s orbitals 2s and 2p orbitals interacting in such a fashion that because of sp mixing, you have the sigma pulled lower in energy. But in this case, no such sigma was like there. No such pulling down was there because 14 electrons or less followed the same order as your N2. याद है कुछ कि भूल गए? Till N2 you actually form S और S जब मिलते हैं तो क्या बनाते हैं? Sigma S and Sigma S star. P and P when they form, you know that PZ, which is along the internuclear axis, forms your sigma and sigma star, और PX and PY क्या बनाते हैं? Pi PX, Pi PY, Pi PX star, Pi PY star. Bonding and anti-bonding orbitals. ठीक है? So here in this case, when you talk about carbon monoxide as a ligand, what it does is, I have told you that your metal atoms will get combined to any of the ligands via a sigma bond. This sigma bond is formed समझ लो इसको, सिग्मा आपको पता है इज बाय द डायरेक्ट ओवरलैप अलोंग द इंटरन्यूक्लियर एक्सिस, ठीक है। ये वाला सिग्मा बॉन्ड कैसे बनता है, बिकॉज ऑफ डोनेशन ऑफ इलेक्ट्रॉन डेंसिटी फ्रॉम CO। लिगेंड का तो काम ही यही है, लिगेंड क्या कर रहा है, इट इज गिविंग द इलेक्ट्रॉन डेंसिटी टू द वेकेंट ऑर्बिटल्स ऑफ द सेंट्रल मेटल एटम। सो what will this CO do, it will donate electron density to the central metal atom. So because of that a sigma bond is like formed. This bond between metal and CO is not only said to possess sigma character, it is also believed that it possesses pi character as well. Sigma plus pi character. तो pi कहाँ से आया, where does this pi come in from? Because carbon monoxide का if you remember the electron configuration, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then you have the p orbitals getting filled. There you see that the pi star, that is the pi anti-bonding orbital is vacant. And क्योंकि pi anti-bonding की energy similar to the metals d orbitals energy, तो metal में जो filled electron density है, जैसे if I talk about nickel, what is nickel? It is 3d8 4s2 generally in +2 oxidation state. So then it will just be 3d8. So उस केस में हमारे पास 1 2 3 4 5 6 7 and 8. Carbonyl is a strong field ligand. You know that carbonyl is a strong field ligand. So in that case, if you just carefully look at it, then what happens? These are like filled d orbitals. So they are also capable of giving energy back to CO, ठीक है। CO तो दे रहा है क्योंकि वो ligand है, ligand has the property of donating electron density to the metal। अब क्योंकि metal के पास भी थोड़े से electrons, it has orbitals which are filled with electron density, because this energy of 3d orbitals is similar to the pi star anti-bonding orbital of CO, तो क्या होता है, दोनों की एनर्जी सेम है, ये खाली बैठा है तो ये थोड़ी सी इलेक्ट्रॉन डेंसिटी विल बी शिफ्टेड फ्रॉम द मेटल बैक टू CO. Do you get that? And because of this back donation of electrons, you get a pi character introduced. That is why in many of the entrance examination questions you get which of the following acts as a Lewis acid. Lewis acid क्या होता है, Lewis एसिड बेस थियोरी क्या थी, अगर इलेक्ट्रॉन पेयर देता है तो बेस, अगर इलेक्ट्रॉन पेयर लेता है तो एसिड। सो इस केस में इफ CO is taking electron density back from the metal atom, then it will be called a Lewis acid. So CO acts as a Lewis acid. I repeat it again, कार्बन मोनोऑक्साइड की MOT एक बार दोबारा देखना, to just provide some oiling to your mind, ठीक है। उस केस में you will find that the anti-bonding orbitals of CO are left vacant. Those pi anti-bonding orbitals of CO जो पहले नीचे खाली होगा उसी को पहले भरेंगे ना, तो pi is lying lower in energy than sigma anti-bonding. So because pi anti-bonding is similar in energy to your 3d filled orbitals of metal, तो ligand despite giving electron density to the metal which forms a sigma bond will take back some electron density from your metal filled d orbitals. So metal will pass on electron density from its filled d orbitals to CO, and this will be called as, this will contribute to the pi bond character. So you have a combination of sigma as well as pi bond in the chemistry of metal carbonyls. And let me tell you, this is also studied in a separate branch of chemistry which is known as organometallic chemistry. You are not doing it in details, but you understand that if we are talking about carbon monoxide, तो अब carbon monoxide बोलते ही याद रखना, this is a ligand which acts as a Lewis acid. Why as a Lewis acid? It will accept density from the central metal atom. So it's like a reverse trend, and from which part of metal? The filled d orbitals, and it will donate to the vacant d orbitals. So this kind of an effect is also known as synergic effect. This is also known as a synergic effect. Synergic का मतलब ही होता है friendly. I give you something and you give me something. So if I am teaching you, I expect you to get more marks and to clear your entrance examinations as well. So you understand, this is some kind of a synergic effect. I have my own interests, you have your own interests. So when metal is giving something, when the ligand is giving something to the metal, this time it is taking back the electron density also from the metals, which gives the sigma as well as pi bond character. CO is generally tagged as a Lewis acid because it can accept electron density back from it. So today we've by and large talked about only two theories, that is one, the valence bond theory, and second, the crystal field theory. We have seen in details as to how to talk about the hybridizations. Valence bond theory will help you for the entrance examinations despite having so many limitations. ठीक है, उसमें लिमिटेशंस है, पर लिगेंड जितने नंबर है, कोऑर्डिनेशन नंबर जितना भी है मेटल का, उसको देखते ही यू कैन प्रिडिक्ट दी हाइब्रिडाइजेशन. देन यू जस्ट हैव टू शॉर्टलिस्ट बेस्ड ऑन द कैरेक्टर ऑफ द लिगेंड, और लिगेंड का कैरेक्टर मेजरली आपको कहाँ से पता चल रहा है, CFT से. So for your theory, both VBT, CFT are very, very important. CFT also has certain limitations. Now go through them, because it considers your ligands to be point charges when you know that they are not acting as point charges. So one limitation is that. Then there are several more limitations that you can think about, but utilize both of them properly to understand and solve as many questions as possible. This is one of the most easily comprehensible, and I'm sure that you all have understood. So solve these questions and you will be sending back the answers to CBSE in another 2 days. Clear? Thank you. लेकिन वो ले रहा है ना, लीगेंड का तो काम ही है, वो तो देगा ही देगा.